Welcome, everybody, to Quantum Science and Quantum Technology, an event that will showcase some of our work and some of our thinking around this incredibly exciting topic. We're particularly pleased to see so many of our alumni and our friends in the audience today, and also many new faces. So I'll give a brief introduction, and then we'll be followed by three of my remarkable colleagues. Please use the Q&A box from the start to pose questions, and we'll take your questions at the end. It may not be possible to answer all questions in real time, but we will endeavor after the event in the following days to write to each of you with a full answer to your question. So, black body radiation and the photoelectric effect gave birth to quantum mechanics, which told us how electrons move in metals. And this became Quantum Revolution 1, because it gave birth to the transistor, to microelectronics and advanced communication, ultimately leading to global positioning systems, to MRI, to the laser, and to exascale computing, and the mobile or cellular phone. There is a growing realization that we are entering a second quantum revolution. The first quantum revolution enabled us to exploit quantum matter to build devices. The second quantum revolution enables us to engineer large numbers of quantum systems with full control of the quantum state of the particles, for example, entanglement, Einstein's spooky action at a distance. The best known example of a quantum technology today is the quantum computer. Google's quantum supremacy was a milestone, but a useful quantum computer is far into the future. But nonetheless, this milestone was significant because it taught us that it's not impossible to build a quantum computer, it's just merely extremely, extremely, extremely hard. And whilst the quantum computer is perhaps the best known of these technologies, there will, in the future, be a massive range of quantum-enabled devices that will turn our highly technological civilization that's been created by Quantum Revolution 1 into something we could not even imagine. Rather similar to, if you go back to 1947 and think of the discovery of the transistor. And the transistor, the original transistor, was a very small thing like this. And in the days when that transistor was invented, nobody would have imagined that in the future, there would be devices like this mobile phone or cellular phone with incredible numbers of transistors in them and the incredible number of things that it can do. And in the future, there'll be quantum-enabled mobile phones. And if you ask me what they can do, I would be not able to tell you. And the people that invented the transistor in 1947 could have conceived of the mobile phone and its capabilities today. This is the Beecroft building in Oxford. It's one of the most isolated buildings from its environment in the world. We sometimes call it the quietest place in Europe. And this building will help us to usher in Quantum Revolution 2. This is a picture from 2016 when the building was being built. It begins with a very deep hole, 30 meters deep. and we filled the base of that hole with a block of concrete, a slab 30 meters by 20 meters in extent, incredibly massive, to damp down vibrations from the environment. And in that basement, where we placed that concrete slab, we then placed upon it other slabs that varied in mass from 30 to 80 tons, about the size of a dining room table. And we placed those blocks onto springs in such a way that they were isolated from the vibrations that could get into the large concrete slab. And so the springs take out more of the vibration, and the tops of those blocks, called kill slabs, entered the lowest levels of laboratories. And on the tops of those kill slabs, we then place optical tables that isolate them even more from the vibrations, until we arrive at instruments that we place on the optical tables. And this structure is so impervious to the environment that the surface of the optical table at 10 hertz will oscillate with an amplitude that's less than about 0.2 nanometers, which is atom scale. And this enables atom scale experiments. Now, as a particle physicist, I saw, and my community saw, the developments taking place around quantum revolution too. And we realized it could play a very big role in fundamental physics. And we're not alone in this. Our colleagues in atomic and molecular physics thought similarly. Now, through careful measurement, through observation and deduction, the particle physicists in this world and the cosmologists in this world have developed a remarkably successful prevailing theory of the universe, the standard model of particle physics and the standard model of cosmology. And in the case of the first of these, it's highly predictive to a degree such that it has been rigorously tested, in some cases to 1 part in 10 billion. But as we look around us and at our universe, we realize that that theory that took a century to make needs to be developed further to explain all of the things that we see. The potential today is to revolutionize our knowledge again. Because despite the huge success, there are deep and fundamental mysteries that are unanswered, for which, following traditional methods of exploration in the fields of particle physics, is unlikely to be enough. And new quantum technologies are needed as well. Some of these mysteries include, you'll recall, the remarkable discovery of the Higgs boson, predicted in 1964 and found by us and other colleagues in 2012 at CERN. The Higgs boson and the Higgs field that permeates all of space enables atoms to exist. It's fundamental for us and for our universe, but it is a profound mystery that we do not understand. Dark matter challenges our understanding as well. When we observe the motion of stars in galaxies or the motions of galaxies in clusters of galaxies, we cannot explain that motion simply by the pull of ordinary matter through gravity. There seems to be, for every ordinary gram of matter, another 5 that are dark, and we don't know what they are. We don't know the dark matter quantum. And dark energy, about 70% of the mass energy of the cosmos is involved in driving the accelerating expansion of the universe today, a kind of anti-gravity effect. And this mysterious component, dark energy, and the dark matter make up most of what we know. The visible matter of which we ourselves are composed is just the tip of the iceberg. What we know is a droplet. What we don't know is an ocean, and it is for us and our future generations to explore that ocean, as Newton said a long time ago. Now, in addition to these 3 mysteries, I list here another 7. And we don't have time to discuss these now, but we could certainly answer them during the questions. But everywhere we look, there are mysteries. And to solve them, we have so many possible theoretical choices that we are forced to look at the data and to look at the data in more and more detail than ever before. We're in a data-driven era. And our job is to measure, as Galileo said, what is measurable and make measurable what is not so. And instrumentation is the great enabler of this. It is the great enabler for science that is both pure and applied. And for the science that I do, particle physics, it's absolutely essential because new directions in science are launched by new tools, much more often than they are by new concepts. The effect of a concept-driven revolution is to explain old things in new ways. The effect of a tool-driven revolution is to discover new things that have to be explained. Tools, by that I mean precision instruments, are key to discovery when exploring new territory, and quantum 2 provides those new instruments. So in a data-driven era, quantum 2 has an important role to play. And I had the opportunity to present that pitch to the UK government over the course of 2 years, representing the community of particle physicists in the United Kingdom and international colleagues. And the UK government agreed, and £40 million was invested in a new program in quantum technologies for fundamental physics. This is part of a much bigger program of quantum technologies in the United Kingdom, where the investment is in total pledged or realized already is £1 billion. So within this data-driven era, quantum technologies will play a key role in helping us understand the mysteries that we see and find. And so to give you just two examples, one of the lowest hanging fruit for quantum sensing programs, quantum technology programs, is to discover what dark matter is. The experimental approaches to dark matter detection are highly complementary one to another. The chi here represents dark matter, and the F represents ordinary matter. And if we look for example, at direct detection, looking for dark matter as it passes through the Earth, as it scatters off of nuclei in sensitive cameras deep under the ground. That's one way to find dark matter. Another way is to look for dark matter annihilating in the halo of our galaxy, producing signals that we see when we stare out into outer space. And a third way is to use particle accelerators to take ordinary matter and turn it into dark matter. And we're using all of these approaches, but we have not yet found what the dark matter is. So this is a ruler, and it shows mass in electron volts. In electron volts, a proton is 1 GeV, 10 to the 9 electron volts. You see that represented here as the fourth tick from the right. So dark matter today could be anywhere in the range from the Planck scale on the right, all the way down to 10 to the minus 22 of an electron volt. So searching for dark matter is a bit like building a better mousetrap. That is a mousetrap for a mouse that you've never seen, will never see directly, may be joined by an odd assortment of other mice, and may or may not be a mouse at all. So it's an incredibly difficult piece of work, and the progress that we've made, I'm going to show you now on this scale. So the two main ways that we look at the moment, relying on the particles to come to us rather than making them and looking at them in the cosmos, in the sky, is through searching for one of the two best theoretically motivated candidates, the WIMP. And there we use multi-ton experiments, deep underground, full of noble liquids, and the WIMP, the dark matter, will interact very rarely with the ordinary material of our camera. And because of its great mass, it will cause the nuclei of the atoms in our camera to recoil, and we can detect that. And another way to look for dark matter is to look for extremely light dark matter in tabletop experiments with quantum sensors. And so the progress to date is here. So these two bands show how much of the total possibilities we've explored. And in each case, we're just beginning to get limits that are truly decisive in ruling out the possibility of dark matter in these regions. And yet, we have not, I restate, found dark matter. The potential gain in sensitivity from quantum revolution 2 is shown by the broadband here, and so it will quantitatively and qualitatively change our understanding. So thinking about these light-dark particles, which could be detected with quantum sensing, I'd like to give you a sense of how that works. And so the idea is to make a camera that is incredibly sensitive to the presence of this dark matter. And then, rather like this cartoon, we'll take an axion, and that's the pendulum on the right. And if the pendulum on the left is matched exactly to the frequency of the pendulum on the right, what will eventually happen is the pendulum on the right, on the left, which represents our detector, will actually start to move around in synchrony. And so this is a resonant phenomenon. And there have been recent new theoretical breakthroughs that have motivated new searches for this type of dark matter. A revolution in the theory and the tools of quantum information science has produced sensitive measurement techniques that would enable these searches. The signal from the dark matter waves is coherently accumulated in various types of laboratory oscillator that represent the pendulum on the left. And they can be atoms, they can be cavities, they can be lumped element circuits. In contrast to traditional techniques to detect the impulse from scattering of individual dark matter particles, these types of detector are driven by the collective force from macroscopic numbers of dark matter particles, minimizing the backgrounds in this narrow band detection, and which then requires cryogenics and quantum sensor technologies to reduce the readout noise to an unprecedented level and speed up the searches. And so this is an example of a response that the UK community came up with to the government's opportunity to fund the quantum technology for fundamental physics. It's a consortium called Quantum Sensors for the Hidden Sector. Hidden sector means dark matter and other things that we cannot see. It's a collaboration between the universities shown here. And so this is a cavity-based search, and it relies on the Primakov effect, where the axion, shown on the left, converts to photons that we can detect in an external magnetic field. One tunes the cavity over a large frequency range corresponding to the mass range of the axion. And if the frequency matches the mass, the axion of the axion, then the cavity behaves just like the coupled pendulum on the last slide. And this is therefore a style of dark matter radio. As you vary the frequency, you look for a signal, and maybe you get a blip like that shown in the box in the center. And if that happens, you've found dark matter. Now, these are very difficult experiments to do. There's a very small interaction between the axion and the photon. We say there's a small coupling, and that's the main challenge. And this leads to very long integration times and places a premium on a very large magnetic field. The very slow scanning times are the reason why so little of the possible phase space has been explored for the axion today. And so we will collaborate with the world-leading experiment in the United States, the axion dark matter experiment, that operates the best search to date. And we will help them speed up their searches using technologies developed in the UK. And our ultimate ambition is to build a larger experiment in the UK with a larger magnetic field. And we hope that through this work, the US and the UK and other colleagues will discover dark matter one day. Our contributions, particularly in Oxford, will be to develop ways of detecting and amplifying the photons that are produced by the axion in more sensitive ways and in quicker ways than before. And an example of this are qubits. Qubits developed for quantum computing are excellent detectors of microwave photons. And the qubit states are then changed by the photon absorption, and we can detect that and measure that. A second project that the community has proposed with the money that's been made available is the ION project, the Atom Interferometer Observatory and Network. This project is a close partnership with the National Quantum Technology Hub for Sensors and Timing at Birmingham, and with an international partner, the MAGIS collaboration at Fermilab in the United States. And so the institutions shown here are building a 10-meter atom interferometer, the largest built ever in the UK and one of the largest in the world, in the Beecroft building. And we hope to create a network between Fermilab and Oxford to detect ultralight dark matter and also gravitational waves eventually. Some atom interferometers can be used for the direct detection of dark matter. We hope to build first a 10-meter interferometer in the Beecroft, and then a 100-meter and eventually kilometer scale interferometer in other parts of the country or at CERN. And in the US, there are similar plans for a scale-up. Now, the atom interferometers can be used to directly detect the dark matter over many, many orders of magnitude in mass because they are able to measure a distinctive signature of dark matter, which is that it may cause fundamental parameters such as the electron mass and the electromagnetic fine structure constant to oscillate in time with a frequency set by the mass of the dark matter and an amplitude determined by the dark matter mass and the local dark matter density. And this in turn leads to a temporal variation of atomic transition frequencies. And since the transition frequencies depend on the electron mass and the fine structure constant, this produces a non-trivial signal phase in an atom interferometer when the period of the dark matter wave matches the total duration of the interferometric sequence. In addition to being able to detect ultralight dark matter, these atom interferometers are a new technology for detecting gravitational waves at frequencies that LIGO and in future, the space-based version of LIGO, LISA, will be insensitive to. And whenever one looks at a new frequency range in the universe, one discovers new things. The collaboration with MAGIS involves participation in the design, the commissioning, the operation, the data analysis and searches for new physics, and the co-development of the image detection systems, both for MAGIS and for the UK detector, ION 10. And then ION and MAGIS will be networked together to search for new fundamental interactions and dark matter, and a scheme for the two atom interferometers with a single laser beam in the Beecroft is shown at the right. So I'm really delighted that we're joined today by so many alumni of our department, many of whom I know have generously supported Oxford Physics with donations over the years. We deliver talks like this for you, for free, and for the public for free, as part of our ongoing commitment to share our research with the wider community who ultimately fund it through the taxpayer, and to inspire people with the fascinating and truly immersing world of physics. If, however, you would like to learn more about how you can contribute to our work, in particular by supporting our fund for DPhil scholarships, we call that OxPay, please visit our website. I'd like to extend my warmest thanks to those of you who have supported OxPeg in the recent past via our recent communication to alumni, and especially those who are part of our Henry Moseley circle of donors who are here today. That's now a great pleasure for me to introduce the next speaker, Seamus Davis, who recently joined us from Cornell, where he was the J.G. White Distinguished Professor of Physics. Seamus was drawn to Oxford in part by the remarkable new Beecroft building that I briefly mentioned, which has been constructed, as I said, to isolate us from the perturbing effects of the environment, such that it is the quietest place in Europe. Seamus's intellectual focus has always been on macroscopic quantum physics. He feels strongly that the world is quantum mechanical at all scales, that fundamentally there is no boundary between quantum and classical, except in the human mind. The challenge is to develop macroscopic instruments and techniques to allow human perception and utilization of the macroscopic quantum phenomena all around us, with quantum computers being just the most topical example. Most of his research adventures have involved the invention of unprecedented physics instruments and techniques that allow human perception, understanding and manipulation of macroscopic quantum phenomena. His talk today, he will propose to all of you an analogous program of research for quantum gravity. So Seamus, I've stopped sharing my screen and it's over to you.
Okay. All right, so I believe you can see my screen now. Is that correct?
We can.
Okay, super. All right, thanks very much. Good morning, good afternoon, good evening to everyone. I want to talk about gravitational quantum mechanics. Let me turn this off because it will be, you don't need to see me. So, okay, let me quickly remind you of a couple of things we need to know about gravitational mechanics and quantum mechanics. So we know from Newton's work that if you use Newton's 1/r² law of gravitation, you can understand virtually all the mechanics of what happens in our solar system. One thing Newton was very well aware of is that you can't understand how the force gets from the sun to the planets. And another thing which is less well known is that Newton didn't actually measure the strength of gravity. That was Cavendish. It took Cavendish's what was then the most sensitive experiment in the world 250 years ago to measure the magnitude of the gravitational interactions by directly measuring the force of gravity between, kilogram scale objects in the lab. All right, now that's gravitational mechanics. How about quantum mechanics? So Schrödinger, the key proposal is that every particle has wave-like characteristics. So a particle traveling through space has a wavelength, which goes as 1 over its momentum. And for example, if it reaches a barrier with 2 apertures in it, when the wave exits on the other side, it'll make an interference pattern. And we know that this is true because if we measure the probability of detecting the particle, it's high in the regions where the interference pattern is strong, and it's 0 in the regions where it's weak. So we really believe that particles are quantum waves. Now, second thing is quantization of energy. So in our classical world, the energy that an object can have, let's say a mass on a spring, can be anything. But in the quantum world, if you follow Schrödinger's theory, then the energy is quantized. It's some integer times Planck's constant times the angular frequency of the oscillation. But you can only have the system in each of these quantum states. So those are 2 precepts. The third one is how do you get from one state to another? Well, Rabi showed that if you know the energy difference, final state minus initial state, divide by Planck's constant, that sets a frequency. If you send in a signal at that frequency, it'll drive the system from the state where it starts to the second state. And in fact, if you keep the signal on, it'll drive it back to the first state again. Those are Rabi oscillations. That's how you change state. And finally, entanglement, which Ian mentioned. If you have 2 separate systems, then each of them is in a quantum states. Well, that's all there is to it. They stay there. But if they're interacting, then what can happen is you get an entangled state where now you have to consider both things at the same time. One state begins to evolve from its initial state to what the other state was. And the other one begins to evolve from what it was back to where the initial one was. And this entanglement cycle, is when this happens, you're detecting purely quantum mechanical phenomena. This is John Bell, a great Irish physicist. Okay, so based on these 4 elements of quantum mechanics, we have this new quantum information technology revolution, which is happening all around us. Superconducting qubits, ionic qubits, atomic qubits, and photonic qubits are all different hardware platforms for quantum computing. We don't know which one is going to win the race and be the most economical and efficient and powerful. So what that has produced is, high cap investments in many different new companies pursuing different quantum computing technologies. This is the commercial ecosystem of leading companies as of right now. Once such a computer becomes efficient, economic, viable for large-scale computing, then there's uncountable, unimaginable applications which will emerge. We can predict the structure of biomolecules, which is impossible now. Quantum artificial intelligence has already been tested, quantum materials discovery, logistics and massive problems which are otherwise unsolvable, and many economic and national security applications. So there's a massive wave of a quantum mechanical wave of quantum technology approaching and breaking over us now. That's a wonderful thing. But one of my tasks here is to remind you that this does not mean that we fully understand quantum mechanics. There are still deep mysteries. And the deepest of all is the link between general relativity and quantum fields. So here's a schematic of time of our universe from the Big Bang until now. And the evolution of space-time is governed by Einstein's general theory of relativity. On the other hand, all the objects in the universe are governed by a different theory. It's the theory of quantum fields, as far as we know, originally first solved for electrons by Feynman. And the strange thing is that now in almost 95 years of trying, these two theories cannot be reconciled with each other so far. We're missing some key fact. This is a classical theory, this is a quantum theory, and at present, never the twain shall meet. Now, if we look at it in terms of forces, there are four major forces in our universe: electromagnetism, the weak force, which example powers the sun, strong force holds nuclei together or breaks them apart, and gravity holds together solar system, galaxies, and the cosmos. Now, all three of these we know for certain are governed by quantum fields. Electromagnetism, weak, and strong force are governed by quantum fields. We don't know about gravity. We do know that classical gravitational field dynamics now exists. When two black holes spiral in and merge, they send a gravity wave through the universe, which can be detected by LIGO. When these waves are detected, which I hope you can hear here, we know that gravitational is a classical dynamical phenomenon. It's an absolutely wonderful thing. But what we don't know is if that dynamics is related to a quantum field, quantum gravity field. This is the outstanding question to be answered. Feynman nailed his colors to the mast long ago. He said, if you believe in quantum mechanics up to any level, then you have to believe in gravitational quantization. That's pretty clear. Still, 60 years later, we don't have any evidence. So something has got to give. We need to think about why these experiments are so difficult. So imagine you have a particle and it's wave-like, and it's approaching an interference screen, just like I show here. And on this side, there's some kind of an interference pattern. So now we've all come to believe that this is true. We don't really have any difficulty with this concept. We learn it at least in college, sometimes in high school. But think carefully. Suppose this object was a gravitating mass. Suppose it was a cannonball. Still, Schrödinger's theory should be correct. When its wave-like wave function passes through this interference thing, and now there's an interference pattern out here, where is all the mass of the cannonball? Nobody knows the answer to that because we have no quantum theory of gravity. So very recently, just a little bit over 3 years ago, our colleague at Oxford, Professor Vedral, proposed the following ingenious experiment to find quantum gravity. You take two masses on two springs. So they produce, if they're fully quantized, they produce quantum states of the oscillator. But they're two separate oscillators. Now, if the only interaction between these two oscillating masses is gravitational, and if that interaction can be shown to entangle the two particles, quantum entangle the two particles, then he proved, at least to the satisfaction of some members of a quantum gravity field, that if this occurs, that gravitational field is a quantum field. This has become the new objective of this whole field. Now think about what this requires. It requires that you quantize, control, and measure, and then entangle some quantum mechanical particles. So we know from quantum technology that this is eminently doable for electrons and atoms and photons, etc. But is it doable for two objects on the scale of a kilogram that you need to get a large enough gravitational interaction? Well, oftentimes it's said to be impossible. However, this is Oxford, so we take a different view. We have proposed a quantum Cavendish project to address this problem. So consider what's necessary. We need two massive objects on the scale of a fraction of a kilogram, let's say a quarter of a kilogram. And we need to put each in a quantum mechanical state. If they're separated by about a millimeter, then there's a large force between them. Cavendish detected it 250 years ago. On the other hand, in order to be able to manipulate this system, we need the oscillator frequency to be around 100 hertz. So it sounds like this. And we need that for both oscillators. If that's the frequency, then the energy splitting between two states is about 10 to the minus 31 joules. If we don't want random fluctuations of temperature to overwhelm these states, we need a temperature near 10 nanokelvin. So we know what the spring constant is required. We know the position sensitivity required. The other thing we need is that vibrations of the whole apparatus won't move the state from one state to another. So we need an ultra low temperature and ultra low vibration environment in which we can mount these two masses proximate to each other. Now, that has long been viewed to be impossible, given the scale of these numbers. This vibration level is about 1 billion times quieter than the quietest place you have ever experienced. However, as Ian said, we have the Beecroft building. Our labs are down here on the northeastern corner, 30 meters underground. In those labs, we can build our cryostat on top of this isolation block, about 30 tons. Our cryostat weighs about 15 tons. And the level of isolation is such that for us, by the time we get on board the cryostat, the motion, vibrational motion, is near the diameter of a nucleus. And this is not just an artist's conception. These photographs were taken yesterday in the Beecroft. Here's the B3 level. Here's those vibration isolators. Here's the keel slab. And sitting on top of this slab, here's our isolation table. So we already know from measurements that this isolation is working extremely well. Now, the other thing we know lead is ultra low temperatures. This is Nicholas Curti. He was a professor at Oxford for much of his career after the Second World War. And he introduced nuclear demagnetization refrigeration. What he showed is if you take something like a massive object, 10 kilograms of copper, you cool it down to quite a low temperature, 10 millikelvin, in a very high magnetic field. So far, so good. But in doing so, you align all the nuclear spins of the copper piece, then you open this heat switch, making this object so that no entropy can enter this object, no heat. And the nuclear spin entropy is then given by the magnetic field divided by the temperature squared. But it can't change. So if you reduce the field from, let's say, 12 Tesla to 12 millitesla by a factor of 1,000, then what happens is the temperature follows it down from 10 millikelvin to 10 microkelvin. I've built 3 of these machines. They are amazing, and they really work as advertised. You can cool an object which is so big, it's heavy, it's hard to lift into the temperature range near 10 microkelvin. However, we need 10 nanokelvin. So the last step is, so here's our 10 microkelvin platform. Suspended from it is the mass of interest. Now we use a position sensor to find where the mass is, measure the displacement of the mass, turn up a large gain, change the phase of the signal, and feedback on a force such that when the mass moves up, the force pushes it down. When the mass moves down, the force pushes it up. If the mass is jiggling due to the high temperature, turn on this feedback system with a gain of a few hundred or 1,000, and it'll suppress the vibrations into the nanokelvin range. Again, this is not as strange as it sounds. It's exactly the same technology as you use in a Bose sound suppression earphone, except that it's about 1 billion times more sensitive and more powerful. And indeed, we know from many experiments that this vibration suppression cooling works to cool things into the quantum state. So let's assume that we can find the resources and build the apparatus to carry out such a gravitational quantum mechanics experiment. So we have already built the first cryostat on the basement level of the Beecroft building, as I showed you. We'd have to build the nuclear demagnetization part. We haven't done that yet. If we had built that stage and cooled to 10 microkelvin, then we'll build this experimental apparatus. You can ignore the details. It's just two vertical, you can think of them like rulers, rigid metal bars, upon which are mounted two heavy masses such that they can oscillate in this direction. They're going to be the quantum oscillators. We cool down this stage to 10 microkelvin, and we can suppress the vibrations as required because it's a Beecroft building. Then we use feedback cooling to cool each of these masses into their quantum states. That's the concept. If that works, if we manage to use feedback cooling, and there's no physical reason to imagine that this wouldn't work, because it's worked many times in the past. I've done it myself, but not to an object this massive. We would then be cooling an object of mass on the scale of a kilogram into a temperature range near 10 nanokelvin. That would be a world record by a factor of around 1 million of the largest object, which is demonstrated to be quantum mechanical. As Ian said, I believe everything is quantum mechanical, so I believe this is going to work. Second thing we need to do is to avoid the Heisenberg uncertainty principle. If you keep measuring the position of this object, you'll destroy the experiment because you can't observe the thing you want to measure. So what we need to do is keep the measurement system turned off, but when we're ready, close the switch, carry out the measurement, which will tell us how much energy was in the device from the measured oscillation. This also would be a world record. And last but not least, we believe we should be able to change the state of this massive object by using Rabi oscillations, which are driven electrostatically by applying a voltage between these two electrodes. So far, so good. Those are the tools that we would need to proceed. If we could build and demonstrate them, we would have satisfied the conditions to quantum mechanically control and measure gravitating masses. Once we reach that point, we enter unknown territory because the experiments on the gravity involved have never been carried out. So the first thing we'd like to try if we reach an operating instrument, and instruments are the basis of all new physics, I completely agree with Ian on that, is to produce gravitationally driven, to drive the Rabi oscillations with the gravitational field. So we would oscillate this mass at a frequency which should change the state of this mass, okay? And then at an appropriate time, measure whether or not we have raised this guy from this state to that state. And if the answer is yes, we would have produced gravitationally driven Rabi oscillations, which would be a major first, a major step forward for gravity physics, for quantum gravity physics, and a first in any experimental apparatus. Now, it might fail for the following reason. Roger Penrose, who is one of our colleagues, has proposed that if you have one massive object, you can put it in a quantum mechanical state, and it'll stay there. It'll remain coherent until you measure it. And then by doing the measurement, you will know that it was in a coherent state. So far, so good. But he hypothesizes that if there's a second mass nearby, it's not doing anything, it's just existing. But if it exists, the quantum dynamics of the quantum gravity field of this object will decohere the second guy, and it'll only be found it destroys the quantum coherence of the system. It'll be found in the ground state. If we actually observe this, it would mean many of our other proposals are going to fail. On the other hand, it would be a great success because we would be able to test Penrose's hypothesis that the source of decoherence in quantum mechanics is gravity. Okay, is gravity, which is an amazingly strange and interesting hypothesis. All right, however, let's assume for the sake of argument that his hypothesis is not borne out. Then the third experiment we would like to do is to cool this mass into one state, cool that mass into the other state. From the design of the experiment, we know how strong the gravitational interaction is, and we could measure it directly anyway. So since we know how strong the interaction is, we would know how long to wait before these two guys would become entangled. And then by measuring them both, we could demonstrate that they are entangled. If this experiment gives a positive result, it would be a huge breakthrough because it basically means that gravitational field is quantum mechanical. And last, coming to my last slide now, the last experiment we would like to do is this Penrose-Gedanken experiment, which is really mind-bending. So this is a cartoon of just two masses. The detector mass, this one, and the source mass, this one. But he proposed to put the source mass in a superposition of two different locations. Now that's actually possible. There is a so-called coherent state that you can create in a mechanical oscillator, quantum mechanical oscillator, so that for large parts of the dynamics, the mass of the object is at two different locations. Under those circumstances, you know, what will gravity, whose source is at two different locations, do to the detector when measured? Well, nobody knows, not even Penrose. Any outcome to this experiment will be revolutionary because it'll reveal a new experimental fact upon which we have no logical conjecture at the moment because we have no quantum theory of gravity. Okay, so here's the summary. The Oxford Quantum Cavendish project wants to take just bring the first light to bear on the issue of what is the quantum mechanics of gravitation. We can propose to do that because of the extraordinary capabilities built into the Beecroft building. The designers were geniuses. And furthermore, our ability to build ultra low temperature, massive refrigerators upon which we should be able to cool this object to nanokelvin temperatures. If so, we want to do a sequence of experiments to answer this last key outstanding question about the forces of nature. Is gravity quantum mechanical? Thanks very much for listening to me, and I would be delighted to take any questions later.
Thank you very much, Seamus, for a fascinating talk. So there are plenty of questions coming up, and we'll be asking you them later, as you anticipate. And so now we move to the next speaker.
All right, let me stop share.
Yeah. Wonderful colleague, David Lucas. David is a professor of physics here at Oxford and a tutorial fellow at Balliol College. His research in atomic physics has covered precision measurements to search for new physics, the use of ultra-cold atoms to model statistical physics, and for nearly 20 years, the manipulation of individual trapped atomic ions to form qubits and quantum logic gates, the basic elements of quantum computers. He demonstrated with colleague Andrew Steen the UK's first quantum logic gate in 2005, and the research group has gone on to develop some of the best qubits and logic gates in the world. He is currently the principal investigator of the UK hub in quantum computing and simulation. And today he is going to give a brief introduction to the basics of quantum computing and the state of the art. Thank you very much, David.
Thanks very much, Ian, for that introduction. It's a pleasure to be here, and thanks to so many people turning up in the audience. So let me just share some slides. And I hope that is appearing for everyone. So yeah, I guess I'm going to be talking a little bit about the building blocks of quantum computers, or the kind of technology that we use in my research group, which are single atoms, single trapped ions, and a little bit about the sort of state of the art of the field. And Seamus has already given a brief introduction, and Ian as well, on this quantum 2.0 so-called revolution. Quantum computing is just one part of that, and as Seamus says, there's a lot of companies getting interested. So quantum computing as an idea has been around for a long time, and of course question everyone wants to know is, why don't we have quantum computers yet? And I guess the answer is they're very tough to build, and we're really in a sense at the beginning of that quantum computing revolution, but it's pretty exciting. Anyway, so let me step back and think about quantum information computing. And of course, the way you normally hear about this is popular articles and so on, is the idea of quantum computers being in some sense very, very powerful because of the enormous capacity of an entangled quantum system involving lots of entangled particles. So Seamus was just telling us about the possibility of entangling massive particles gravitationally, which is of course very exciting. But what we're dealing with in quantum computing is individual quantum particles, like going down to a single atom. And what we'd like to do is entangle in a very, very controlled way those individual atoms. So I'll tell you a little bit about how we do that in a moment. So quantum computing, in a sense, is this huge capacity you have in quantum systems, like a sort of huge memory, bigger than anything you could possibly build, even if you built a conventional computer out of all the atoms in the known universe. And the existence of discovery of powerful quantum algorithms for able to solve certain particular mathematical problems, such as factorization and searching, classic examples that were early discovered, but there are doubtless many other applications, probably many which haven't even been discovered yet. But so that's the computing side of it. As a physicist, I think what perhaps drew me to the area is a bit more the sort of intrinsic physics interest of studying these entangled states in a controlled way in the laboratory. How do we actually build up that control, using the technical term coherent to build quantum superpositions atom by atom? How do we understand and overcome the sort of noise of the environment, or the decoherence that's all around us? But whether you're talking about the computing or the physics, in a sense, in the lab, what we have to do is the same thing. We have to sort of construct some sort of machine capable of controlling these large-scale entangled states, and that's the so-called quantum computer. And as a spin-off that was perhaps of this technology which was early recognized, and which again the other speakers have alluded to, is the use of these techniques, these new tools, perhaps in searching for new physics, enabling new science. So techniques such as quantum logic spectroscopy, so the most precise atomic clocks in existence now, which could be used for searching for new physics effects, rely on essentially quantum logic gates, ideas that were invented for quantum computing. And it was also recognized early on that quantum entanglement, if you entangle particles, you can increase the sensitivity for certain measurements, which can therefore, of course, make you allowing you to measure things more precisely and to search for new effects that way. But what I'm actually talking about in these systems, here's an image which has been flashed up a couple of times before. It's from one of our labs here in Oxford, and this is a device which is an ion trap. As you can see, it's something that's very much human-sized. It's a centimeter scale device. It was built right here in the workshops of the Clarendon lab. But I love this photo, which was taken by David Nadlinger, one of my graduate students, a few years ago, because it unites the quantum and classical world in one photo, and it's not a mock-up photo. If you look right in the center there, just side where my laser pointer is, then you should see a bright little dot, and that dot is one single atom. And when you think about that for a moment, if you've not seen that sort of thing before and you're not familiar with this, that should amaze you. And you think that, you know, in your little finger, there's whatever Avogadro's number, 6 × 10⁻³ atoms, countless billions of them. The fact that we can isolate one, hold it still in space and see it there is a very impressive technological achievement of lab science. it's actually become pretty routine. People have been doing this for the last 30 years or so for all sorts of purposes, such as atomic clocks and precision measurements, but also this individual quantum system, the atom, makes a wonderful quantum bit, and quantum computers are made out of quantum bits, qubits, as we call them, and quantum logic gates. And in some ways, the photos are rather misleading because the atom looks millions of times bigger than it actually is. It's it's just the size of a single pixel there. It's a little bit like looking through a telescope at a very distant star. The size of the star depends on the properties of the telescope, typically not the star, but that is the light, the fluorescence light coming from a single atom. The reason you can see it is that there's a laser beam shining through there, and you can't see laser beam at all because this device is all in an ultra high vacuum apparatus. And so this really is the sort of the vacuum tube or valve era of quantum computing, perhaps. I'm going to tell you more about qubits and logic gates in a moment. I must acknowledge it and say a little bit about who funds us for this work, and set a bit of context, and that's just briefly mention the sort of quantum technology landscape we're in. Here in the UK, we're part of the UK's National Quantum Technology Programme, which was one of the earliest of many such national programmes, started in about 2014 with an initial investment by the government of 270 million in various areas like a National Physical Laboratory and student training hubs, things like this. But it also included 4 research hubs, and one on computing was led by Oxford, also included about 8 or 9 other universities, but led by Oxford, and that was called the NKIT, or Networked Quantum Information Technology Hub, and there were other hubs of quantum sensors, quantum cryptography, quantum imaging. And a key ambition of the UK programme was to start to push this research out of labs into, in quotes, the real world, and that's been happening in the hubs through partnerships with lots of industrial partners, and also formation of spin-out companies, such as Oxford Quantum Circuits here, Oxford Ionics, Universal Quantum down at Sussex University, and so on. We're now in the second phase of this UK government programme. Our computing hub is now called QCS, Quantum Computing and Simulation Hub, and the UK is also has established and launched the National Quantum Computing Centre, which is quite exciting. That's going to be built a few miles down the road from Oxford at the Harwell site there. And of course, similar programs internationally. The EU has a quantum flagship program for $1 billion, started a couple of years ago. The US National Quantum Initiative, similar scale investment. So there's a lot of work going on all around the globe in this area. And these are some of the different hardware platforms that people have proposed and are actively researching for quantum computing. And we're actually pursuing all of these across the quantum computing and simulation hub in different labs across the UK. I'm going to be very parochial. I'm going to tell you about my own work. I work in trapped atomic ions with my colleague Chris Ballance, who's going to talk after me. So this is a different kind of ion trap here. Looks a bit more like some sort of chip-based device, and that's the idea. It's a more scalable device to hold ultimately more qubits. Superconducting circuits are the other very mature sort of quantum technology at the moment. This is what Google and IBM are pursuing, but also in recent years, silicon-based qubits have made some great progress. And people are also looking at so-called impurity spins or nitrogen vacancy sensors in diamond, and also purely optical quantum computing using single photons of light in optical chips like this. I've just color-coded these sort of different technologies. Typically, the blue labeled ones here usually operate at cryogenic temperatures, whereas the ions and photons here typically operate at room temperature, which is also obviously something of a technical simplification. We can do that because we use a beautiful technique here that the individual ions themselves are cooled by laser cooling, a completely different method of cooling to what Seamus was just describing. but they're cooled down to similar sort of micro Kelvin temperatures above absolute zero, even though they're sitting just a hair's breadth above this room temperature surface here. That's something that gives us the first step in the exquisite control that we need to manipulate these qubits. So here's a typical qubit. That's trapped calcium ions. As I say, that's one single atom of calcium. And why does that make such a good qubit? Similar reason to why it makes a great atomic clock. Atomic clocks are how we define time, and how we do that is we choose two different energy levels or energy states, quantum energy levels in our atom. Let's label them 0, 1 here, and they're separated by an energy which is h f naught, so call that h being Planck's constant. And of course, being a quantum mechanical system, those of you know anything about quantum mechanics know that this can exist in a superposition state. This is Schrödinger's cat superposition, and I can write this wave function in this sort of superposition state here. The thing I want to draw your attention to is that e to the I phi there, and that phi or phase angle is equal to 2 pi f naught t. It involves this frequency or energy splitting between these two states. If this were an atomic clock, I'd be using that to define time. The requirements for qubits and atomic clocks are rather similar. In the context of a qubit, I really need to know what that phase is. That's part of my calculation, if you like. It needs to be well controlled. This needs to be a very, very stable energy splitting, just as I would need and use in an atomic clock. So on the other hand, here's some of the requirements we need for clocks and qubits, and their similarities and differences. And obviously in a clock, you're after ultimate frequency precision. In a qubit, 10 to the minus 12 precision will do. You know, that's part per trillion. So, you know, it's non-trivial, but it's perhaps 1,000,000 times easier than the state-of-the-art atomic clocks. On the other hand, we need to be able to prepare the qubit in a particular quantum state and detect which state it's in with better than 99.9% precision. We need to be able to control the qubits using those Rabi oscillations that Seamus talked about, with something like 4 nines of precision or 0.01% of error, if you think of it that way. And we want to be able to do this ultimately on thousands, possibly even millions of qubits, quantum bits. And that we need to control them individually, whereas some of the best atomic clocks right now are based on just one single atom, like in my picture there. So those are single qubits. Let me try and give you an idea of how we make 2 of those qubits interact via a quantum logic gate. And that's how we can generate on demand, deterministically, when we want to, an entangled state. So here's the scheme. In one of our ion traps, these green blobs are ions. We've got 2 ions trapped in an ion trap, and we're shining on here some laser beams on these ions, which set up a sort of interference pattern in the light here. And the key idea is that the laser beams can exert a mechanical force on these atoms. And if you think back to Ian's nice video he showed of the 2 pendula, I have one pendulum swinging and exciting the other pendulum. Although we're in the quantum regime here, something very similar is going on here. We can think of these atoms really like masses on springs, again, extremely small masses, and the laser beams exert force on them. And the crucial thing is that the direction of that force depends on whether my qubit is in its 0 or 1 state, the 2 possible states of the qubit. And so the force will be to the left or the right, depending on that internal state of the atom. And what we do is we shine this force on. It's this interference pattern here provides an oscillating force. I'm shaking this mass on the spring, and I do that near a resonant frequency. And I can arrange things such that if the qubits are in opposite states, so one is in the 0 state, one is in the 1 state, or vice versa, basically nothing happens, that it won't jiggle around. But if they're both in the same state, both 0 or both 1, what happens is it really excites the motion, just like a mass on a spring. I can excite the motion for a little bit and damp it down again. And the quantum mechanics says that when I do that, the wave function is really pushed around, it's really moved around, rather like a mass on a spring. This is an illustration of what the quantum mechanical wave function is doing in these different qubit states here. And if I arrange things just right, I get a sort of operation truth table here for my quantum bits, where these two states which undergo the motion pick up, here again is a quantum mechanical phase, e to the I pi by 2 is my phase that I'm trying to pick up here. And this is rather like, it's very similar to a convention, what's called an exclusive OR gate in conventional electronics. So that's how we do quantum logic gates with these single atoms. I hope I've given you a flavor of that. One of the beautiful things about our trapped ion qubits is that we can see the effect of this entangled state that we can build here in a very visual way. So let me show you some videos of instead of animations like this and cartoons, let me show you the real thing in the lab. So this is a movies made by two of my colleagues, Amy Hughes and Vera Schaefer, made a beautiful video of the operation of this kind of entangling gate. So we just have two ions here. There they are, they're filmed. This is more or less sort of real time, what you would see if you're looking at this. And what we're doing is applying over and over again a quantum logic gate to generate this entangled state here. It's just like the entangled states that Seamus was talking about, that he may or may not see in his gravitational experiments. We're producing this superposition state. It's called a Bell state, named after John Bell, who Seamus introduced you. And you can see that in this superposition state, either both atoms are in the 1 state or both in the 0 state. And the way we see that in a very direct way here is that they either fluoresce, they're either bright or dark. So when they go away, those atoms are still there. They're just in the opposite state. And when measuring this system, we get one or other result. In fact, you can see one frame of the film where it went wrong, and you see one bright, one dark. So that's our imperfectness of the operations we have. And we can transform this to a different sort of entangled state that looks like this with so-called single qubit operations. And you can see now I get the other effect where I measure either one bright and dark or vice versa. And these are both different kinds of entangled states. That's visualization of entanglement. And it's a real movie right from the lab. I'm now going to take you back in time, I guess, in a sense, to give a little bit of history of the field, quantum computing, but really just to try and show you the enormous progress that people have made over the last 20 years or so. So let's go right back to the beginning. So quantum computing was invented right back in the early 1980s. David Deutsch here in Oxford really came up with the concept of the quantum computer. Richard Feynman in the US had proposed something very similar a year or so before. And at first it was rather a theoretical curiosity. Deutsch was essentially showing a different way of manipulating information. And people started to get very interesting when Peter Shaw, working in the US, invented an algorithm that could break the most powerful codes that we use on the internet all the time, and say the military uses this so-called public key cryptography, which is, as far as we know, unbreakable on traditional computers, essentially because they can never be powerful enough. And he showed that you could do that efficiently on a quantum computer. So that was very exciting, but the problem seemed to be that no one knew how to deal with the inevitable errors and imperfections that would creep into these systems. So Shaw then invented, and independently Andrew Steen here at Oxford invented something called quantum error correction, which is a way of dealing with these errors. And that was a crucial development there, because that really turned the quantum computer from a sort of theoretical pipe dream into something that could actually be built. That was the good news. The bad news was that the implementing this and doing it requires very precise operations and lots of qubits, which we still don't have yet. But at that stage, people started looking for physical systems. It was actually these gentlemen, Sirach and Zoller, working in Innsbruck, who proposed ion trap quantum computing. These control of single atoms as a method for implementing the theoretical ideas of quantum computing. And then at the National Institute of Standards and Technology in the States, Dave Winan and Chris Monroe and their colleagues actually were able to demonstrate the first quantum logic gate in about 1995, 1998. And since then, people have been working on really improving that. So here's the kind of almost the entire history of the quantum logic gate demonstrations. Anyway, it's not really quantum computing, but this entangling quantum logic gate, which is really our sort of fundamental operation we need. And you can see the precision here increases as we go downwards. The errors are getting smaller. And over the years, there's this sort of, this is a logarithmic scale. It's a little bit like a Moore's law progress in the precision of these quantum logic gates. We in Oxford were able to demonstrate what was at the time the most precise logic gate a few years ago. This is the black data points using trap time qubits, and the blue ones down here using superconducting qubits. People in more recent years, the reason people get excited about this is because for many years these results were in a regime where, according to theory, it would be impossible to build a quantum computer. So maybe if you get below this 99% level, it's kind of theoretically possible, but enormously impractical, because you would just need too many qubits at that level of precision. And when you get to this regime where we're just getting into now, it's arguably practically possible to build quantum computers. That's why we're in a very exciting time. There's a lot of investment, as Seamus mentioned, from different companies and different startups and so on. One thing we've been doing recently, by the way, I have to mention, and Chris will talk a little bit more about this in a moment, is that all these demonstrations here use the mechanism I talked about, where essentially you've got ions very close together, a few microns apart in the same ion trap. One thing we've built over the last few years is the UK's first quantum network experiment, where we're actually taking qubits in separate, completely separate apparatuses on either side of the lab, which we call Alice and Bob, and they have an optical fiber link between them. It's a quantum optical link based on single photons, with which we can entangle ions very, very much further apart. And this is we believe, going to be crucial to scaling up systems in the future. So this is a sort of summary of some numbers. So it's just a bunch of numbers here, but achieved in a particular ion trap apparatus right here at Oxford. And what's perhaps significant here is that we've been able to get all these basic operations that you need. It's like a sort of unit cell of a quantum computer, to be able to get all those operations at the sort of precision level required on paper to build future machines. That doesn't mean we're home and dry, of course. At the moment, this is only a system which is has been demonstrated with 2 qubits and so on. So the job of scaling things up further is still a huge but very exciting challenge. One particular thing we did here, by the way, is we did the logic gate operations here electronically instead of using those laser beams I was telling you about. We send electronic signals in here which we can plug in, and of course that's very attractive for thinking about scaling the system up in future. We use microwave electronics, which is a very mature technology. It's in your mobile phone, for example, to do the quantum logic here. So let me just finish by giving some flavor of where we'd like to go in the long term, where we are at the moment. And this is theoretical work of my colleague Andrew Steen, which was, as I mentioned, was one of the guys who invented error correction, of really sort of what performance numbers you need to get to. How many qubits do you need? How small do your errors need to be? And what we're trying to do here, the holy grail, if you like, the ultimate, the long-term goal, is to have a universal quantum computer, just like our conventional computers can do any information processing. And it needs to be able to cope with these errors. It needs to be so-called fault tolerant. So if your errors are very small, that's down here on this axis, and you start scaling the system up to larger numbers of qubits, you go in this direction, you get into this area where your computer can do many operations. Okay, so there's a logarithmic plot. So you can do 10 to the 10, 10 to the 20 operations. So that means you can do a lot of calculations. You get right up here, you can essentially carry on forever. But if your errors are too big down here, no matter how many qubits you have, you can never do anything very interesting. So where are things at the moment? So that the numbers I just showed you on single qubit operations are comfortably in the sort of regime we need to be in, this sort of 10 to the -4 error rate. These are just numbers picked out for typical recent numbers from these two different technologies, superconducting qubits and trapped ions. The multi-qubit operations are more challenging, as you might imagine. And here's the sort of rough state of the art, and here's Google's 53 qubit demonstration, which is, he mentions, a fantastic milestone. But at the moment, the qubits are too noisy. These errors here need to be smaller to get over into this regime. But so we're very much down here on the plains, looking up at the foothills of this mountain that we need to climb. But as I believe Chris will tell you in a few minutes, even down here, actually, even if we can't get to this kind of holy grail of universal computing, even down here in the foothills, there's some very interesting work we can do. So I shall finish there, take you back down to the lab to look at this extraordinary picture of single atoms to remind you of what we're dealing with here. And I will hand over to Chris.
So, David, thank you for a marvelous talk. And so remember, audience, questions will be answered at the end of the session. And so we now go to our final speaker. And so it's a great pleasure to introduce Chris Ballance, who is a UKRI, that's a United Kingdom Research and Innovation Fellow in Quantum Computing. And this is a singularly prestigious award that Chris has received in recognition of his incredible work to date. And he's only at the very beginning of his career. His research focuses on controlling quantum systems with exquisite precision, working at the boundary between quantum physics, quantum engineering, and computer science. He seeks to corral ever larger collections of quantum particles to his bidding, fighting against the natural disorder of the universe to build up Schrodinger's cat atom by atom, while keeping it both dead and alive. A couple of years ago, Chris founded Oxford Ionics, a startup that is commercializing his research and is bridging the chasm between today's scientific curiosities to the full-scale quantum processors that will revolutionize computing. Today, Chris is going to talk about the state of the art in quantum computing and discuss the hurdles that have to be overcome to get useful quantum computers. Thank you, Chris.
Thank you, Ian. So what I want to talk about today is when can we get to the point where quantum computers will be useful? And I'm using a careful definition of the word useful here. So what I mean by useful is getting to the point where they can solve problems that we both want to solve, as well as that can be solved only by a quantum computer. And by only by a quantum computer, I mean in a way where a classical computer couldn't possibly solve them, even if we gave it hundreds to thousands of years. So to motivate quantum computing a bit more, you've heard a nice introduction to it by both Dave and Seamus. But to give you an idea of why this is so exciting, I just want to talk about one of the applications, which is quantum chemistry. So it's a well-known joke amongst physicists that all of chemistry was solved by about 1930. After we have Schrodinger's equation, we can write down the quantum dynamics of our electrons and protons and neutrons in a molecule or a complete person or the world. And all we have to do is solve that equations to understand everything about chemistry. But despite the fact we can write down this equation, we can't solve it. If we try and solve it on a normal computer, what we find is that as we add more and more atoms, the runtime increases exponentially. So what this means is with a standard calculator, you can calculate the quantum dynamics of a few atom molecule. With a supercomputer, you can calculate a medium-sized molecule. But by the time you get up to a complex molecule, perhaps like a protein or a drug molecule, the computing time goes incredibly large. So it can take billions of years by current models to calculate the quantum dynamics of one of these systems. And that's impossible. There's very few problems where you want to know the answer to, and you're willing to wait a billion years for the answer. So with quantum computers, however, we know of algorithms which don't scale anywhere near as badly. In fact, they scale polynomially rather than exponentially. So what this means is that even if classical computers get much faster, we still don't think we'll be able to solve anywhere near this kind of problem on a classical computer. Whereas the quantum computer only takes a marginally longer amount of time to solve this kind of problem than this kind of problem. So as well as chemistry problems, there's many other types of problems we know there exist far faster solutions on quantum computers than classical computers. So examples of this are things like optimization, optimizing portfolios, optimizing routes, or things like machine learning. So we know there are empirically ways to make machine learning faster by using quantum computers. So the question is, when will we get to a useful quantum computer? When will we get to this point here where the only way to solve a problem that we want to know the answer to and can only do it on a quantum computer? So at the moment, we're over here. We have quantum computers, they work. However, there are no problems yet that anyone wants to know the answer to that we can do faster on a quantum computer than on a classical computer. But what I want to tell you today is that we're surprisingly close to crossing this chasm and getting to the point that we can solve problems that we want to solve on a quantum computer faster than on a classical computer. So first, you've probably heard a lot of breathless coverage about quantum computing in the media, and it might be under the impression that quantum computers are already done, the physics has already tidied up and cleaned up, and there's just a few bits of engineering to finish before these things are released in the world. That's not the case, but what we have hit is the really important end of the beginning region, which is that of quantum supremacy. So you've heard Ian mention this already. So quantum supremacy is the point where a quantum computer has been shown to solve a problem that can't be solved on a classical computer. So this is subtly different from it being useful. Because with quantum supremacy, the program is just chosen to be as hard as possible for the classical computer and as easy as possible for the quantum computer. So for this problem that Google achieved on their device a couple of years ago now, they're essentially generating random patterns of random numbers, but they expected to be able to generate a different pattern from a quantum computer and a pattern that's very hard to generate on a classical computer. So essentially they generate a noise spectrum, and the structure of this noise spectrum is unique to a quantum computer. And what they showed is that they could generate this noise spectrum in just a couple of minutes on their quantum computer, and yet it would take 10,000 years to do the same thing on a modern supercomputer. So this is the first existence that quantum computers really can do something faster than classical computers, despite the fact the problem they're solving isn't very useful, and also despite the fact that they get the answer wrong about 499 times out of 500 times they run it. So this is an incredibly important scientific breakthrough, but there's still a tremendous amount of work left to get from here to the point of solving useful problems faster than a classical computer. So here's a few devices that are about at the state of the art in quantum computing at the moment. So these devices on the left are built out of trapped ions, the technology that David's already talked about. And the devices on the right are built out of superconducting qubits. And what you can see is that they have quite a range in the number of qubits. So the Honeywell devices over here have 10 qubits, all the way through to the Rigetti devices with 128 qubits. But the qubit count doesn't measure everything about a quantum computer. To make a useful quantum computer, you need to take these qubits and you need to make them interact. And the more qubits that you have, the more interactions you need to make between the qubits in order to generate these very large entangled states. And in fact, you need something like n squared interactions to make n qubits interact in a useful fashion. So if we instead measure how many qubits we can apply n sequential measure gates on and still measure roughly the right results and measure this as useful qubits, we see something quite interesting. The Honeywell device with the smallest number of qubits has 9 useful qubits. The IBM device with 65 qubits only has 7 useful qubits. And the other 2 devices don't even have enough published data to estimate anything more than just a handful of useful qubits. So what this means is we can't just rely on the qubit count. To make useful devices, we really need to get the errors down. So we need to have 3 things in a useful quantum computer. We need to have a large number of qubits, and we need the qubits to be able to interact with very low error. And this error we require gets lower. We have tighter bounds on how sloppy we can be at making the devices as we increase the number of qubits. And we need to have these qubits being well connected. All of the qubits must interact with all of the other qubits to be able to solve interesting problems. So then the question is, we have 10 useful qubits. How many qubits do we need to solve a problem that's useful rather than just chosen to be hard for a classical computer and easy for a quantum computer? And the answer to that is we just don't know at the moment. At the moment, we estimate somewhere between 50 qubits and 100 qubits is the regime where we can start doing interesting problems that can't be solved on a classical computer. But it could be as many as 1,000 qubits we need. What we know for sure is that it's more than 50 qubits, since if we have about 46 qubits, we can solve that problem on a classical computer. And we know that every time we add a qubit, we double the size of classical computer we need to solve the problem. So what we know is that for sure by 50 qubits, no supercomputer around for the foreseeable future will be able to solve it. So we know it needs to be more than 50 qubits, but probably less than 100 to 1,000. And part of the reason for this uncertainty is because the state of quantum computing algorithms is improving so fast. So a decade ago, some of the quantum computing chemistry calculations I've talked about, even for a trivial system, would need something like 1,000 qubits. But over the last few years, as the software has improved, we've taken that qubit requirement down from, say, 1,000 qubits to more like 10 qubits. And indeed, we can now simulate these simple molecular systems on state-of-the-art quantum computers. So the best quantum computers here with the most useful qubits are built out of trapped ions. And this is the technology I use both in my research in the university and in my company. So you've already heard from David why these make good qubits. We have these beautiful isolated particles that we can drive very clean interactions between. And we can trap them in devices like this that are microfabricated, that have many electrodes on, which then allow us to trap individual atoms above the surface of the device and then manipulate them very cleanly. And because the qubits are individual atoms that are trapped not in the mechanics, in the physics, in the surface of the device, but trapped several tens of microns above it, they see a very clean environment. They're essentially perfectly isolated individual atoms. So what we need to do is work out how we can get from these handful of qubits we have now to the, say, perhaps 10 qubits we have now to hundreds or thousands of qubits we need to get into this useful regime. And this is what a lot of my research is based around. So what we can't do is just put more qubits in exactly the same device without changing anything. For sure, we can put them in there and we can manipulate them, but what we observe is that as we put more qubits into a single register, the errors get worse. And remember, we need the errors to get better as we put more qubits in to be able to access all of them and make a useful device. Otherwise, we end up in this state of having very many qubits, but not being able to do anything with them. So instead, what we have to do, what we're forced to do, is break up the qubits into a series of different registers. And then we need to exchange information between these registers to make all the qubits being connected. And there's a couple of different ways we can imagine doing this. The first is to put many different registers on one chip. And we can do this by putting many electrodes on the chip and then adjusting the potentials so we have different registers stored in different potentials. And then by changing the voltages on these electrodes, we can physically move the qubits around and move them between registers. So this way we're physically moving the information across the chip by physically moving the atoms of the qubits. The other way of doing this is by not moving the atoms themselves, but just by moving the information. And we can do this over, say, a quantum network by coupling the atoms, the qubits, to photons, and then piping these through optical fiber. So my research works around both of these, and I'm going to talk a little bit about how we can do both of these in order to make, and in fact, are driven towards needing both of these to make very large-scale devices. So this is a picture of an ion trap chip taken from above. It's in color. The trap's actually made out of gold, so it looks just as beautiful as this in real life. This is made by my colleagues in the US. And this is a chip that contains many different registers of qubits. So what you see along here are our electrodes. And these underlined sections are all the different places where qubits can be trapped. And indeed, you can imagine trapping many different registers of qubits all over the chip like this. However, in order to drive the operations forward on these qubits, as David mentioned, most people use laser beams. So if you use laser beams on these devices, what you have, as soon as you start going to these non-trivial geometries, is you have terrible problems designing geometries where the laser beam can manipulate just one register of qubits and not interact and interfere with all the other registers of qubits around. So this is one of the major limitations in scaling up the devices this way. So in fact, this chip here was made in 2010, over a decade ago, which is an eternity in the quantum computing landscape. And yet we still, as a community, haven't got these devices under control. And one of the reasons is the difficulty of wiring up so many laser beams to control these devices. So one of the areas my company focuses on is trying to get rid of many of these lasers altogether. So here, for example, we have a couple of qubits we want to entangle. And then rather than shining a laser beam over the device to drive the entanglement, we instead now know how to drive this entanglement forward using just electric current in the devices. So this is a much weaker interaction, but with specially designed electrogeometries, we can make this interaction strong enough to drive entanglement between the qubits. So what this means is then we can drive forward entanglement without having to put lasers across the surface of the chip, just by having currents flowing through the device, which then means in much the same way as we can have many different electrodes around here to control the physical location of the qubits, we can have many different electrodes to drive the entangling gates forward. And also these electronic currents are compatible with standard CMOS technology, which then means we can integrate the control electronics into the chip itself and imagine having very large scale chips. It allows us to control many qubits. So with these techniques alone, we can then just wire this all up and get rid of the laser beams from almost all locations of the chip. So with these techniques alone, we think we can probably get to 100 qubits in the device in the near term. And this is possibly enough to get into the useful regime. But really, we want a way of getting beyond that. And what we don't want to do with these kind of devices is have to throw away and redesign the engineering every time we increase the device size. So this is very much what happened with classical computers in the Cray days in the 1970s. An architecture was designed, it was pushed as large as possible, then it was all thrown away and then built up from scratch again to make larger processors. So instead of doing that, we want a way of building devices that are as big as we can plausibly do with the technology and then connecting them together. And that's where networking comes in. So the idea of networking quantum computers is this. If we take these two ion-trap quantum computing devices that are physically separated, here they're two separate apparatus, two separate devices, the qubits can't be transported between them. What we can do, though, is use the fact that atoms couple very strongly to light in a quantum way. So we can take these atoms, we can generate them in an excited state and let them decay. And after we do this, we get a photon emitted. And if we do this right, that photon is entangled with the spin state of the atom. And after that photon's entangled with the spin state of the atom, if we guide it into an optical fiber, we now have entanglement between our quantum computing register and the light, a flying qubit. And if we do the same in two devices at once, we can then connect these devices together over optical fiber, over a quantum network, and put them into a quantum measurement device. And then after this device measures these photons, it can project the photons into an entangled state. And then by quantum back action, this projects the qubits into an entangled state. So like this, we can have two physically separate quantum computers that are connected just by optical fiber in the same way as a standard computer network is connected together, but quantum, and then swap information between devices. So now we can imagine taking many of these devices, which we think we can build up to 100 qubits, and then just being able to replicate them. And this is something that engineers can do very well. We know how to make identical devices and make many of them. And if we do this and can connect them together by optical networks like this, we have a foreseeable path forward, not just to get to thousands of qubits, but to get to tens of thousands or hundreds of thousands with engineering improvements rather than physics improvements. So this is something we've been pursuing quite hard in the university labs at Oxford. And this is an example of an apparatus in the university lab to give you a taste of what these things look like. So this apparatus is now the highest performing quantum computer network in the world. So here you can see an apparatus over here, Alice, and then an apparatus over here, Bob. So these devices are pretty large. They're about a meter across this dimension. But the actual quantum core is very small. So the chip here is only a couple of millimeters across. And of course, the individual atoms above it are even smaller. So what we expect to see over the coming years is that we can miniaturize these devices down by several orders of magnitude. And then you can imagine having data centers full of these things So very small quantum processes connected together via optical fiber so we can network them together. And this is exactly what we do with classical computers nowadays. We know that it's crazy to try and build custom processors. When you want a new data center, you don't try and build a larger processor to get a larger supercomputer. Instead, you just have many thousands of standard cores off the shelf and you connect them together over fast, efficient networks. And this is the dream. So to summarize, I just want to go back to the history of classical computing. So classical computers took a very long time to develop, from the first ideas of the analytical engine by Babbage back in the 1840s, through vacuum tubes and relays to transistors to integrated circuits. And it's past here when people really started feeling the impact of classical computers. So, but the first useful classical computers were way back here. So if you think back to, say, Colossus at Bletchley, just up the road, these systems were highly specialized. They were designed to solve just one problem, a very important problem of code breaking. And despite the fact they're specialized and could solve just one set of problems, they did this incredibly well. And this is about where we are with quantum computing now. We're just at the point where we can see these very specialized applications coming over the hill. And we expect that in the coming 5 to 10 years, we're going to start solving them. And we're just starting to reach this really exciting frontier where we can start to do stuff on a quantum computer that we predict we can't do with anything else in the world. And we can probe the frontiers of physics. We can build these entangled states that don't exist in nature. And this, as a physicist, is tremendously exciting to me. So with that, I'd like to thank you.
Chris, thank you very much for a wonderful talk. That's been 3 wonderful talks. And now we have just a small amount of time for some questions. And so there were a massive, massive number of questions that were asked. And because of that, I would just select a few that I think are of particular interest to everyone. And one of them concerns, and it would be for Seamus, and I'm dialing through all of the different questions all the way back to a very early question. And it was about, how do you get your funding for your work?
So the Beecroft building and the development of the ultra-low vibration facilities were funded by Oxford University fundraising, primarily through Adrian Beecroft, but other donors as well, and also the university's resources. With respect to building a quantum Cavendish experiment, it's a rather unprecedented proposal, and so far we have not been able to find a funding source for that program. However, hope springs eternal. We're still pursuing another opportunity, and if that doesn't work, we'll continue to pursue it. And I'll cut this short right now, but just to say in general, the more unprecedented the idea is that you propose, in fact, the smaller is the probability that you can get funding for it. And that's really a tricky problem in frontier research in any science. Okay, thanks.
Thank you very much for that answer, Seamus. So now we'll take one for David. So I'll dial back down through the long list of questions. So I have to make a choice here between a number of remarkable questions. And the question is, can we use quantum entanglement for speed of light communication?
I guess you mean before faster than speed of light?
Yes, right. It would be before faster, yes.
Yes. No, but I believe not. So yeah, quantum entanglement has this very interesting property that even if I separate the particles, their quantum states are related in a way that, such if I measure one, then measure some properties of one of the particles, then I in some sense immediately influence the outcome of a measurement on the other particle. But it's not in any way that can, such that I can use that for transmission of information, so far as we know. So it's more like the properties of the particles are correlated when the particles are close together, if you like, and if you take them further apart, those correlations remain. But the interesting thing, I guess, about that entanglement is that the it's a correlation which is very different from a classical correlation of two classical particles, and it can't be mimicked. I really have to throw away the idea that these atoms are independent of each other if they're in an entangled state. I really have to think holistically about the quantum mechanical wave function really involving both of them, even if they're light years apart.
I'll give you one more question because it was asked almost immediately afterwards, which how do you choose the particular atoms to be the ions in your qubits? Why those ones?
That's a great question. So there's quite a few different atoms you can use. It's partly a technological question actually about the lasers that we need to manipulate the atoms. But most of our experiments use either calcium or strontium atoms. And if you think of your chemistry, they're in group 2 of the periodic table. They've got two valence electrons, the neutral atom. We take one electron off, that means you've got one valence electron, and that gives it a relatively simple atomic structure, having one electron there, and that means fewer lasers, and also the laser wavelengths, that is the color of the lasers we need to manipulate calcium, both calcium and strontium ions. Very, very convenient actually. Also convenient for sort of future miniaturization and scalability, because it's the kind of lasers that were developed. It's blue diode lasers that were developed for DVD Blu-ray players 20 years ago. So there's the miniature semiconductor lasers that we can use, which are very efficient devices.
Thank you, David. And now one for Chris. How do the errors occur in qubits?
So essentially, the difficult thing is making the errors not occur. The errors occur very naturally since everything interacts with everything else. This is the rule of quantum mechanics. So when we try and build a quantum computer, we're really trying to build a very isolated system where our qubits don't interact with each other when we don't want them to. And then only when we want to, when we call for entanglement between certain particles, do we turn those on. So essentially, this is the breakdown of the isolation. For a quantum computer, we want an isolated system where we can turn on and reach in from the outside and make very strong interactions. And in pretty much every physical system, this is not the case. And we have to work very, very hard in the lab to make these systems sufficiently isolated. And the errors occur from just imperfect control and imperfect isolation. And this is inherently a trade-off in how well you build your device. Yes,
there's actually sort of a related question that came in around the same time, which I think I'll ask you as well, which is about whether there is in the world now, a stockpile essentially of quantum algorithms in existence ready to solve real world problems, just waiting for the engineering of sufficient qubit count. Or do we still have to write most of those algorithms? Is it a significant hurdle?
Yeah, this is actually a really good question. So at the moment, there are lots of algorithms we know that we get very good speed up on quantum computers, and lots of algorithms we know that we seem to get good speed up on quantum computers, but we can't prove it. We just know it in our bones that it feels good. But there's still probably a tremendous number of problems that we don't know. And essentially we're in the regime now where we're writing programs for machines that don't yet exist. And if you can imagine how hard programming a normal computer is, if not just you don't have one of these on hand, you don't know even if they will exist, it's tremendously interesting. So I still believe that the killer application for quantum computing, we don't know yet, but it'll be something else coming around the corner. And that will only really start to get this when we get into the quantum exploration regime of having computers we really can play around with and try things out on.
That's a great answer. Thank you. Because I asked both you and David 2 questions, I'll come back and ask Seamus one more as well. This came in during Seamus's talk. He said you're considering such large objects. And isn't it the case that you have to worry about how they will interact with the building around you from a gravitational sense? And would there be any merit in putting your experiment, Seamus, in space? You're muted, Seamus.
Sorry about that. So with respect to the environment, Oxford University and we have invested an enormous amount of effort to make sure that these experiments do not interact with the vibrational or acoustic environment in which the lab lives. The experimental instrument is in a doubly sealed room. It's like a Russian doll. And once experiments are running in those rooms, no human being enters for many months. So although protection from the environment is critical, that part of the problem is already solved. That's a really good thing. Second thing is that outer space. So people have a perception that outer space is very quiet. But if you ever put a microphone on the space station, you'll find out that outer space is very loud. So I would stay away from it.
Well, I think on that note, I want to thank all the speakers for wonderful talks, very, very informative. I'd also like to thank the audience who have stayed with us throughout this time, almost 2 hours now. And that conveys really how important and how interesting this work is. I apologize to all of the people that we couldn't ask questions of live. And there are nearly 100 of you. So what we will be doing is we will be writing personal answers to all of you over the next few days. And in addition to that, of course, this recording will be put online and these slides will be made available to all of you as well. So with that, I'd like to say, I hope you and your loved ones stay safe and well. And we look forward to sharing another event like this one with you in the near future. Thank you very much and goodbye from Oxford.